You know how you catch your reflection and just kind of stop for a second? We see mirrors every single day, right? But behind that simple image, there's this incredible world of physics, light, and geometry. So let's dive right in and figure out how a mirror actually works.
Okay, so it all kicks off with something we call reflection. And it doesn't matter if it's a bird seeing itself in a pond or you looking in the bathroom mirror, the basic idea is exactly the same. Light hits a smooth surface and bounces off, but not just any old way. It bounces off in this really precise, organized pattern, and that pattern is what creates the image we end up seeing. All right, here's the game plan for today. We're going to start with the simple flat mirrors we all know and love, plane mirrors. Then we'll get into the basic rules that make all reflections work. After that, things get a little weird with spherical mirrors. We'll see how they bend reality. We'll figure out exactly how images are formed, and finally, we'll look at where you see all this stuff in the real world.
Okay, first up, the plane mirror. You know, the regular flat one you've got in your house. It looks like it's showing you a perfect copy, right? But is it really a perfect copy? Let's find out.
So here's a fun little real-world puzzle for you. I bet you've seen this 1,000 times. But have you ever actually stopped and thought, wait, why do they do that? The answer is hiding in plain sight, and it all comes down to the physics of that simple flat mirror.
Think about it. A driver looks in their rearview mirror. They need to read that word, and they need to read it fast. The mirror itself flips the text. So by writing it backwards on the ambulance, it shows up the right way around for the driver in front. It's a clever trick, and it points to one of the most important properties of plane mirrors.
Okay, so here's the deal. An image in a flat mirror has 5 key properties. Let's run through them. First, it's upright. It's not upside down. It's the same size as the real object. It also looks like it's the same distance behind the mirror as you are in front of it. It's also virtual. Now that sounds fancy, but all it means is the image just looks like it's back there. You couldn't actually put a screen behind the mirror and see the image on it. And finally, the big one that solves our ambulance mystery, it's laterally inverted. That just means left and right are swapped. Your left is the reflection's right and vice versa.
So how does this whole left-right swap thing, and really all reflection, actually work? It's not magic, I promise. It's all governed by 2 beautifully simple laws. So let's check those out.
Before we jump into the laws themselves, let's just nail down a couple of terms so we're all on the same page. Reflection. We've got this. It's just light bouncing off something. The ray of light that comes in and hits the mirror, we call that the incident ray. And the one that bounces off, that's the reflected ray. Easy, right? Now, here's a super important detail for getting how this works. Look at how we measure the angles. You might think we'd measure from the mirror's surface, but we don't. Instead, we imagine a line that sticks straight out from the mirror at a perfect 90-degree angle. We call this line the normal. So the angle of incidence is the angle between the incoming light and the normal. And the angle of reflection is between the outgoing light and that same normal line. It's all about the normal. And boom, here are the laws. It's just 2 of them. Law number 1, the angle of incidence is always equal to the angle of reflection. No exceptions. They are a perfect match. Law number 2, the incoming ray, the outgoing ray, and that normal line we just talked about, they all lie flat on the same plane, like they're drawn on a single sheet of paper. And that's it. These 2 simple rules are the foundation for everything we're about to talk about. All right, so we've totally got flat surfaces down. But what happens when we start to curve the mirror? This is where things get really, really cool. Let's talk about spherical mirrors. So you've basically got 2 main flavors. First, there's the concave mirror. Think of the inside of a spoon, where it caves in. This kind of mirror brings light rays together. It converges them. Then you have the convex mirror. Think of the back of the spoon, the part that bulges out. This one does the opposite. It spreads light rays apart, or it diverges them. And why does this happen? Well, remember our normal line? On a curved surface, that normal is pointing in a slightly different direction at every single spot, so it bends the light in a very specific, predictable way. Okay, to really talk about these mirrors, we need a couple of geometry terms, but don't worry, they're pretty straightforward. First, just imagine the mirror is a small slice of a giant, complete ball. The center of that ball, that's what we call the center of curvature. Easy. Then, the principal axis is just a straight line that goes right through the middle of the mirror and that center point. And finally, the really important one, the focal point. This is the magic spot where parallel rays of light all come together after they bounce off a concave mirror.
So we've got the rules, we've got the parts. Now let's put it all together and do something kind of magical. We're going to predict exactly what kind of image a mirror will create.
When it comes to concave mirrors, there are 3 super simple rules we can use to trace the path of light. They're like a recipe. Rule 1. Any ray that comes in parallel to that main axis is going to bounce off and go right through the focal point. Rule 2. If a ray passes through the focal point first, it's going to bounce off and go out parallel. See? It's just the opposite of Rule 1. And Rule 3. If a ray goes through the center of curvature, it just hits the mirror and bounces straight back on itself. The cool part is, you only need to draw 2 of these rays to figure out exactly where the image is going to show up. Let's give it a shot. Okay, look here. The object is pretty far away from the mirror, so we draw our first ray, coming in parallel, and it bounces through the focal point. Then we draw our second ray, going through the focal point, and it bounces out parallel. See where those 2 lines cross? Bam! That's our image. And what do we notice? It's upside down, or inverted. It's smaller than the real object. And it's a real image, which means light rays are actually meeting up right there. You could put a little screen there and see it.
Okay, now for part 2. Let's move the object closer, putting it between the center and the focus. We use the exact same rules. A parallel ray bounces through the focus. A ray through the focus bounces out parallel. But look what happened. The image is now bigger. It's still real and it's still inverted, but just by moving the object, we've totally changed the size and location of the image.
Now this table is basically your ultimate cheat sheet for concave mirrors. It sums up all the possibilities so you don't have to draw the diagram every single time. You can just look and see how the image changes depending on where you put the object. And check out that very last row. When the object gets super close to the mirror, something crazy happens. The image suddenly flips upright, gets bigger, and becomes virtual. Sound familiar? That's exactly how a magnifying mirror like for makeup or shaving works.
And this is not just stuff for a science test, you know? This ability that curved mirrors have to bend and focus light, it's used in tons of technology that we see and use literally every day.
Okay, cars are the perfect example. You've got both types of mirrors working together. That passenger side mirror, the one that says objects in mirror are closer than they appear, that's a convex mirror. It bulges out to spread the light, giving the driver a much wider view of the road. Then you look at the headlights. Inside, there's a concave mirror. It does the complete opposite. It takes the light from that tiny bulb and focuses it into a powerful beam to light up the road. 2 mirrors, 2 totally different jobs.
And once you start looking, you see them everywhere. That little mirror the dentist uses, that's concave, to get a magnified view of your teeth. The big bubble mirrors in the corner of a store for security, that's convex, for a wide-angle view. People even use giant concave mirrors in solar ovens to focus sunlight and cook food. And of course, massive reflecting telescopes use them to capture the faint light from stars billions of miles away.
And you know, that really gets to the heart of what science is all about, right? It all starts with a simple question. Something like, why does my reflection look like that? And that curiosity can lead you all the way to understanding the fundamental rules of the universe and creating some pretty amazing technology.
So what's the big takeaway here? It's that all this seemingly complex stuff about mirrors, it all boils down to just a few simple, predictable rules. From the mirror in your bathroom to the Hubble telescope, the physics is exactly the same. And when you understand those rules, you basically have the power to control light. How cool is that? So that leaves us with one final thought. We've seen how mirrors can help us look at our own teeth and at galaxies far, far away. So the question I want to leave you with is this. Where else can this ability to bend and focus light take us? What kind of future breakthroughs are just waiting to be discovered? All starting with a simple, curved, shiny surface.